Section 5.3, the Fundamental Theorem of Calculus. Consider the function y equals f of t, whose graph is shown to the right. We're going to define an area function for f of t with a fixed left endpoint of t equals a and a variable right endpoint where t equals x. So a of x is equal to the definite integral from a to x of f of t dt over the interval from a to b. And again, the key things to note is that the lower boundary or the lower limit of integration is a constant, but the upper boundary or upper limit of integration is a variable. So this area function really is a function because the amount of area will change depending on the value of x. All right, so what does the Fundamental Theorem of Calculus Part 1 have to say about that? It says if f is a continuous function on the closed interval from a to b, then the area function, defined as a of x equals the integral from a constant a to a variable x of f of t dt over an interval from a to b, that area function we're defining will be continuous on the closed interval from a to b and differentiable on the open interval from a to b, and the area function will satisfy the relationship that a prime of x is equal to f of x, or in other words, if you take the derivative of the area function, which is the derivative of the definite integral, you end up with the function inside the definite integral evaluated at that upper limit of x. That's going to be the key piece of the Fundamental Theorem of Calculus Part 1 for us. It's going to allow us to quickly take derivatives of definite integrals. We'll see examples of that in a moment. But another takeaway, if a prime of x is equal to f of x, then that means the area function, which is our a of x. So the area function of x, which is a of x, is an antiderivative of f of x. All right, let's make use of that highlighted portion and see how that works. So find each of the following requested derivatives. Find the derivative with respect to x of the definite integral from 3 to x of the square root of 9 minus y squared with respect to y. So again, coming back up here to this formula right here, that's what we want to use. If you take the derivative with respect to x, then x needs to be the variable, and that x variable is right here and right here. The inside variable, the t, right there, we refer to as a dummy variable on a definite integral. You could change that to any different letter, and it doesn't change the amount of area that you're getting. So the variable in this area function is the upper limit of integration, that x. Okay, so what does the Fundamental Theorem of Calculus have to say about this relationship? It says if you take the derivative of a definite integral where the lower boundary is a constant, and we do have our lower boundary as a constant, and the upper limit is x, which we also have, then the derivative ends up being the inside function with an x substituted in. So this is one of the quickest derivatives we would ever do. It just ends up being the square root of 9 minus x squared. So almost seems too easy. But what the Fundamental Theorem of Calculus is saying to us in a way is that the derivative and the definite integral are kind of somewhat inverses of each other and kind of cancel each other out. We just have this substitution happening where the upper limit gets plugged into the function. All right, so let's look at another version of this that's a little bit more complicated. We want the derivative with respect to x of the definite integral of cosine of x from cosine of x to 1 of t squared over 1 plus t to the fourth dt. So this almost fits the Fundamental Theorem of Calculus Part 1, except for there's a couple problems. The first one is the constant is up top and the x is on the bottom. Well, we can fix that by just factoring a negative out of all of this and remembering from our properties of integration that if you factor out a negative, that reverses the limits of integration. So then this would be from 1 to cosine of x, and then still t squared, 1 plus t to the fourth, and dt. So factoring that negative out just has us swap the limits of integration. That's the first issue. Now we have our variable up top. But the second issue is that it's not just the variable up top. In the place where we normally would have x, now we have a function of x, cosine of x. So how does that work? So let's write a formula for that. So if you want to take the derivative with respect to x of the integral of a from a to g of x, so a function of x instead of just x, of f of t dt, how would that work? And basically what we do is we use the chain rule. And what we've got for our chain rule here is the inside function is g of x and the outside function is f of x, because that g of x is going to get plugged into the inside function. Remember that this x right here got plugged in to the inside function right there. So that upper limit of integration is our inside function. So what happens when you do this? Well, you still have the integral and the derivative kind of canceling each other out, and you still get that f. But now you're plugging in g of x instead of just x. And because of that composition, you have to use the chain rule and multiply by g prime of x afterwards. So this is the chain rule version of the Fundamental Theorem of Calculus Part 1, when your upper limit is a function rather than just the variable x. All right, so what does that mean for us down here? We carry the negative sign down. We take this cosine of x and we substitute that in place of the variable t. So we end up with cosine squared x up top over 1 plus cosine to the fourth x on the bottom. A little bit of a messy square there. Let me clean that up. But we're not done there. We still have to use the chain rule and go times the derivative of that inside function, which was cosine, and the derivative of cosine of x is negative sine x. So just one little bit of simplification. We have this negative on the sign and the negative out front. Those two would cancel. And we can just write our numerator as sine x times cosine squared x, and then put all of that over 1 plus cosine to the fourth of x. All right, so two versions of finding the derivative of a definite integral that come from the Fundamental Theorem of Calculus. One, the easy version, if the upper limit is just the variable x, you just substitute that into the original function meaning the inside of the integral, and you're done. If the upper limit is a function, you still substitute that in place of the variable like we did here, but you have to apply the chain rule and multiply by the derivative of that function as well. All right, so you'll see a few of those in the homework. Now let's move on to the Fundamental Theorem of Calculus Part 2, and this is the game changer for us. This is the huge deal. It says if f is a continuous function on the closed interval from a to b, and f is any antiderivative of that function, then if you're trying to find the definite integral from a to b of f of x dx, you just take that antiderivative of the inside function and you plug in the upper limit first, right there, and then you subtract what you get when you plug in the lower limit right there. So this is going to make finding definite integrals much easier. We're not going to have to take limit as n goes to infinity of the sum as k goes from 1 to n anymore. We're looking at the number of rectangles going to infinity and getting infinitely small. That's going to be gone as long as we can figure out an antiderivative of the inside piece. And if we can do that, then we just plug in the upper and lower limits and subtract. A shorthand, by the way, for the upper and lower limits and subtracting would be to say you take the antiderivative function f of x and you evaluate that from a to b. So this vertical line and then the two limits tells us we plug in the top limit first and then subtract the value of the bottom limit. And again, as we'll see on the next page, this is a game changer. It's going to make finding definite integrals much easier than it has been in the previous sections. All right, let's go ahead and use the Fundamental Theorem of Calculus to make some definite integrals a little bit easier to do. So they want us to evaluate the following integrals. The first one is the definite integral from -2 to 5 of 6 with respect to x. So according to the Fundamental Theorem of Calculus, our main job is to think of an antiderivative for the inside function. So the inside function is a constant 6, so its antiderivative would be 6x, or at least that's an antiderivative. If you wanted an indefinite integral, you'd say 6x plus c, but it doesn't matter which antiderivative we pick, so we just pick the one where the plus c part is a 0 and go with the simplest antiderivative. So in this case, 6x. And then we evaluate that from the lower limit to the upper limit. And what that means is plug in the upper limit first, and then subtract what you get if you plug in the lower limit. So we get 30 plus 12, or 42. And we just evaluated a definite integral there, and we did it super fast. We didn't have to do limits of sums and all of that sort of stuff. Just a quick check here to kind of verify that that works. Let's imagine the graph of this function. So put some scale on there. Let's go from -2 to 5. And the function is y equals 6. So 1, 2, 3, 4, 5, 6. And draw the graph in there. So something like that. And we're going from -2 to 5. So it should be the area underneath that we're getting. And this is 6 units high by 7 units wide, which would be 42. So since this one is a nice, easy shape, we can test it with area, and it seems like it's working out. All right, let's go ahead and try another one, this time trig function. So we're going to try and find the definite integral from pi to 2 pi of cosine of theta with respect to theta. So we need to think of an antiderivative of cosine of theta. So in other words, we need to think of a function who has cosine of theta as its derivative. So that would be sine of theta because the derivative of sine is cosine. And then we take that antiderivative and we evaluate it from pi to 2 pi, which just means that we first plug in the top value. So sine of 2 pi minus what we would get for the sine of pi. And we can do some quick unit circle thinking about that. So sine of 2 pi, that's right here. And sine is the y-coordinate. The y-coordinate in that spot is 0. Minus the sine of pi, 180-degree rotation, so over here. Again, sine is the y-coordinate, so that's also a 0. So we get 0 minus 0, or 0. An amazingly fast calculation there of the definite integral of cosine of theta. Again, with no limits, no sums, none of that stuff. We do get a weird answer, though, 0. So let's look at the graph of this real quick just to make sure that that makes sense. So we'll put in the function that we were integrating, cosine of theta. So we'll just do cosine of x instead of theta because, again, the inside variable is a dummy variable. We can use anything we want for that. And then I'm going to go in and set my graph window, so second window. And what I'm going to use is the boundaries or the limits of integration. So I'm going to use pi for the lower limit and 2 times pi for the upper limit. Because I'm graphing cosine, its values are always going to be between -1 and 1. So for the height, I'll put -1.5 to +1.5, and we should see a decent graph that way. So let's look at the graph and think about why we're getting the 0. So when you do a definite integral, you are getting the Riemann sum limit. And remember, Riemann sums give net area, which means areas for sections like this that are above the x-axis come out positive, but areas for sections like this over here that are below the x-axis come out negative. And it seems like there's some symmetry in this graph. So the reason we're getting a 0 is this section of area right here comes out negative. This section comes out positive. Because of the symmetry, they're equal to each other and just cancel off. And that's why we're getting the 0. So it seems like a strange answer at first, but if you look at the graph, it actually makes sense. All right, let's practice some other versions of this, see what complications come in. Mainly, we just end up practicing antiderivatives and then practicing a little bit of kind of basic algebra with the plugging in and the simplifying that we need to do. All right, so first of all, we're thinking antiderivative here. So we need to rewrite this in a way where we can take antiderivatives better. So the square root of x, I'll rewrite as x to the 1/2. The 1 over x to the second power, I'll write as x to the -2. This way I have both of those pieces written as x to a power, and then I can use the power rule to find the antiderivative for each of them. So that becomes x to the 3/2 over 3/2. But if you're going to put over 3/2, that's the same as multiplying by the reciprocal out front. So that's kind of a speeded up version there. Instead of dividing by that fractional exponent, you can multiply by its reciprocal out front and save yourself a step. And then on the next one, we're going to have x to the power 1 higher, which would be now -1 if I add 1 to -2, and then divide by -1, but that divided by -1 could just be moved out front as a times -1. Again, kind of doing the reciprocal, but the reciprocal of 1 is just 1. So there's an antiderivative. You can check that real quick by taking derivatives and verify that you get back what's on the inside. And then for a definite integral, we then need to evaluate that from the lower limit, which was 1, to the upper limit, which is 3, which again means plug in the upper limit and then subtract what you get when you plug in the lower limit. So we have 2/3 times 3 to the 3/2, and then minus x to the -1. We'll just go ahead and leave that alone right now and put 3 to the -1. That's the first part. That's plugging 3 into the antiderivative. Now you subtract what you get if you plug 1 into the antiderivative, which would be, sorry about that, a little messy, 2/3, 1 to the 3/2 minus 1 to the -1. All right, so doing a little bit of simplifying here. This is 2/3 times the square root of 3 raised to the third power, minus 1/3, because 3 to the -1 is 1/3. Taking this part right here, 1 to the 3/2 is still 1. 1 times 2/3 is 2/3, so that becomes a minus 2/3. And then 1 to the -1 is still a 1, and the two negatives between these two pieces make it a positive, so that becomes a plus 1. Notice that -1/3 minus 2/3 is -1, so that -1 will cancel off that -1, and we just end up with 2/3 times the square root of 3 to the third power. And we could simplify that a tiny bit. That 3 could be moved inside as a 27. That 27 can be split up as the square root of 9 and the square root of 3 over 3. Square root of 9 is 3, so it will cancel that other 3, and we just end up with 2√3. And you can look at that and say that was kind of a messy one, but is it really? Is it messy compared to taking the limit as n goes to infinity of the sum as k goes from 1 to n of f of x sub k star times delta x? I think if you, in your mind, compare it to that, you're not going to consider this one to be a messy one anymore. All right, let's look at another one. The definite integral from 1 to 6 of x squared times x minus 1. Remember, we don't have a product rule for antiderivatives, so we need to get rid of multiplication. So we're going to do the distributive property there. Make this the integral from 1 to 6 of x cubed minus x squared with respect to x. So just distributing to get rid of the product. Now we have just powers, so we can use the power rule. This is x to the 4 over 4 minus x to the third over 3, and then all of that is evaluated from 1 to 6. So we just need to plug in the 6, subtract what we get when we plug in the 1. So plugging in the 6, we get 6 to the 4th over 4 minus 6 to the 3rd over 3. And then from that, we subtract what we get with the 1, which is 1/4 minus 1/3. Yes, those 1s are raised to the 4th and the 3rd, but that will just leave us as with a 1. And then I'm going to show you a little trick here, but I simplified this in the calculator, and I got 3025 over 12. It can be a little bit of a pain to do the fraction work there. I mean, it's doable. You just got to get a common denominator and do all the addition, subtraction. But, 6 to the 4th and 6 to the 3rd, we got some pretty big numbers there. So let me show you a quick calculator trick for how to do that. So I'm going to go to the calculator, go back to the main screen, and I'm just going to type in what I want to calculate. 6 to the 4th divided by 4 minus 6 raised to the 3rd divided by 3, and then minus 1/4, and then it's a minus 1/3, so that would be plus 1/3. So I'm just entering it all in and pressing enter and getting a decimal version. And then if you want to convert that to a fraction, you can do that by going to the math menu. So just below the green alpha key, it says math, and the very first option there is store to a fraction. So if you just calculated a messy thing and got a decimal and you hit store to a fraction, it'll convert that to a fraction for you. So there's that 3025 over 12, which is the same thing that I had here in the notes. So you can do the fraction work, but I don't mind if you've done the antiderivative and you've done all the plugging in and you've shown me kind of like what the answer looks like and what the pathway is. If you want to speed up the fraction work by using that store to a fraction feature on your calculator, feel free to do that. All right, now that we have an easier method using these antiderivatives to find the values of definite integrals, let's go back to the topic of area and look at an example. So find the area of the region bounded by the graph of f of x equals x cubed minus 1 and the x-axis over the interval from -1 to 2. So they've already shown us a graph of that. Here's our left boundary, -1, and here's our right boundary, 2. And then, importantly, we've got this spot right here at 1, where the function switches over from being below the axis to above the axis. So you might be tempted to just do the definite integral from -1 to 2. But if you do that, the area that's below the axis will cancel out the area to the right, and that would be net area. But they're not asking us for net area. They're asking us for area, regular area, which means that we want to treat the area as positive. So we have two portions of area. We have this part right here that's below the axis, and then we also have this part up here, which is above. So what I'm going to do is find those two separately and add them together. So I'm going to let this one be area 1, and then this one inside and below, that's going to be area 2. So the area that they're asking us to find is expecting us to get a positive value for both of those and add them together. So we're going to find A1, we're going to find A2, and we'll add them up. Let's start with A1 because it is the easier one. So for area 1, you'd want to find the definite integral from 1 to 2 underneath the function, and the function is x cubed minus 1 with respect to x. So if we find the value of this definite integral, we'll have that orange area over there. So if we do that, we want an antiderivative. So antiderivative of x to the 3rd is x to the 4th over 4. And the antiderivative of a constant is that constant times x, so just minus x. And then we evaluate this from 1 to 2. So we do the plugging in, see what we get for that. So we have 2 to the 4th over 4 minus 2. And then we plug in the 1. 1 to the 4th, which is 1 over 4 minus 1. And if you simplify all that, let's see, we have 16 over 4, which would be 4 minus 2. 1/4 minus 1 would be a negative 3/4. So we have a 2 from here. 2 negatives make a positive, and we have another 3/4. So that will be 2 and 3/4. So that orange area is a positive value, 2 and 3/4. Now we want to go after the green area. And the temptation is to just say that A2 is equal to the definite integral from -1 to 1. That's our left boundary and our right boundary for the green area of x cubed minus 1 dx, and just go from there just like we did above. But the thing that we have to remember is that definite integrals compute net area. And we weren't asked for net area, we were just asked for regular geometric area. Net area comes out negative, regular geometric area is always positive. But the net area that comes out negative is equal to the opposite sign of the positive area we want. So when we know the area we're computing with the definite integral is going to come out negative and we know we want a positive, then all we have to do is change the sign of that integral. So we'll put that negative out front, and that's going to make sure that we come up with a positive area because, again, the integral will be net area, which is negative. From here, we just do the same work that we were doing above. So I'll just leave that negative out front, take the antiderivative, which is x to the 4th over 4 minus x, evaluate that from our lower boundary -1 to the upper boundary of 1, and now we just start doing the simplification. The negative just along for the ride, so I'll put that out front and do some brackets, and then do the x to the 4th over 4 minus x. We're going to first plug in a 1 to that, so that'd be 1 to the 4th over 4 minus 1, and then subtract what happens or what we get when we plug a -1 in. That would be -1 to the 4th over 4 minus a -1. All right, so we just need to simplify that down until we get to a number, and then we'll have our A2. So the negative is out front. We have 1/4 minus 1, which is -3/4. And we have minus, and then what's going on in this other one? The -1 to the 4th would be positive, so that's 1/4. The two negatives right here will make a positive, so that becomes a +1. And now looking at what we have a -3/4 minus 5/4. That would be -8/4. So this is negative of -8/4. Two negatives cancel, and 8 over 4 is just a 2, and that 2 represents the green area. Notice that if we did not put the negative out front, we would have gotten -8/4, so we would have gotten a negative answer instead of a positive one. When we're asked for net area, that would be fine, but when we're asked for just area, that is geometric area, which needs to be a positive answer. All right, so going back to the original question, which is find all of the area bounded between the function and the graph, we said that would be A1 plus A2. So that's going to be 2 3/4 for the orange plus 2 for the green. So that's going to be 4 3/4 overall. So there's our final answer. Area that they asked for is 4 3/4. All right. So now we were being careful not to do net area that whole time. And now if we look at the next one, it does say find the actual net area. Now if they had asked us that question first, then I would just do that in a very straightforward way. I would say that the net area is equal to the integral from -1 on the left all the way to 2 on the right of our function, which is x cubed minus 1 dx. I would find antiderivative, x to the 4th over 4 minus x. I would evaluate that from -1 to 2. So that's what I would do if they just asked me for the net area right away. But rather than doing all that work right now, I also know that net area is to take the positive area and subtract the negative area. So that would be A2, the positive orange area up above. Sorry, I think that was A1. So I'll make that switch. The orange area was A1, that's the positive piece. So just take that and subtract the negative portion, which was the A2. And just color coding that. So we did that one in the green. And so we end up with the A1, which was 2 3/4, minus the A2, which is 2. The 2 part cancels. We just end up with 3/4 And there's our answer for net area. And we throw a little shading on there, and then that's a wrap. So you can check the definite integral from -1 to 2 if you want. You'll see that you get the same thing because definite integrals will automatically subtract the negative portions from the positive. So net area is automatic with the definite integral. You can just go from left boundary to right boundary. But if they ask for just regular area and you have switches from below the axis to above the axis, you have to separate those as separate integrals. And the one that's below, you have to make sure that you change its sign so that you get a positive answer, because the definite integral for that below portion will come out negative. It's a little tricky at first, but we're going to do it a lot and you'll start to get used to it. All right, let's go ahead and look at another graphing example. Find the area of the region bounded by the graph of f of x equals cosine of x and the x-axis over the interval from -pi/2 to pi. So first thing, they're just asking for area, not net area. So we do have to think about what sections are above the axis and which are below. So let's start by looking at our boundaries. -pi/2 to pi. So -pi/2, cosine of -pi/2, let's look at unit circle. So just quick unit circle idea. -pi/2 is up here. Cosine is the x coordinate. Sorry, -pi/2 is this rotation, so that's down here. But still the same answer. The x coordinate, which is cosine down there, is 0. So this right here is the -pi/2. That happens to be that point of intersection, which is kind of nice in terms of that being right on the border instead of in the middle of our integral somewhere. And then we're going to pi. So if you rotate around to pi, cosine is equal to -1. So that would be this low spot right here. So that value is going to be the positive pi. So there's our two boundaries on the curve, going from -pi/2 to pi. So the real key is this spot right here. Because we're asking for geometric area, we have to separate the positive above the x-axis portion from the negative below the x-axis portion, do those as separate integrals, and then add them together. So we need to find where that spot is. So that would be a spot where cosine is equal to 0, somewhere in between -pi/2 and pi. So that would be this rotation right here, gives you an x value of 0, and that would be pi/2. And pi/2 makes sense because we're looking at that value is between 1 and 2, and pi/2 is 1.57 roughly. All right, so same idea as before. We've got two areas to find. We'll make this one area 1. This is kind of a straightforward one that's going to come out positive already because it's above the x-axis. But we'll call that portion area 1. And then we have this other portion, which I'll go ahead and do in orange. I think it's the opposite coloration I did on the previous one, but that's all right, as long as we keep track of it. So this area we want to find as well, but that area is going to come out negative if we do a straightforward integral. So we'll have to make sure we change the sign of that. All right, so the area that we want is going to be area 1 plus area 2. Area 1 is going to be the definite integral from -pi/2 to +pi/2 of cosine of x with respect to x. And then I'm starting to put a plus sign, but we're actually going to want to subtract the integral from pi/2 to pi of cosine of x dx. And again, the reason we're going to want to do the minus there is because this definite integral right here represents the net area for that A2 region, which will come out negative. So putting that negative out front is going to make those two negatives cancel and become this addition that we actually want. So let's go ahead and set that up and evaluate it. So antiderivative of cosine is sine. So we want the sine of x evaluated from negative pi over 2 to pi over 2. And then we're going to subtract sine of x evaluated from pi over 2 to pi. Seems very messy, but we've got the unit circle there so we can think about all of these quickly and come up with, I think, pretty nice answers here. So sine x evaluated at pi over 2, we'll go ahead and write it all out, I guess. So sine of pi over 2 minus sine of negative pi over 2. That's our first piece. And then we're going to subtract sine of pi minus sine of pi over 2. All right, so let's start plugging these in real quick. So do a little bit of highlighting. Sine of pi over 2 is up here. Sine is the y value. Up there at that top spot, that's a 1. So sine of pi over 2 is going to be a 1 minus sine of negative pi over 2. And sine of negative pi over 2 is down here, so sine is a negative 1. So we get 1 minus a minus 1. And then minus sine of pi. Pi is right here. Sine is the y-coordinate. The y-coordinate of that spot is a 0. And then minus sine of pi over 2, which we already said was a 1. So right here we get 1 plus 1, so 2, minus a minus 1, so 2 plus 1, or 3. So the overall area, and we'll do that in yellow, I guess, the overall area that they wanted us to find is A1 plus A2. A1 was 2 units. A2 comes out as negative 1 as an integral because of the net area, but we know they want a geometric area, so we changed its sign, and those two negatives gave us a positive. So A2 is positive 1, A1 is positive 2. Add those together, we get our net area of 3. All right, moving on to one last example, and this one is about displacement and total distance. So suppose that a particle moves along a straight line with velocity defined by v of t equals t squared minus 3t minus 18, where t is between 0 and 9 and velocity is measured in meters per second. Find the displacement at time t and the total distance traveled up to the time t equals 9 seconds. So for displacement, you just want to know where did the object start and where did the object end. So this one actually can be done pretty quickly. For displacement, we're just going to take the definite integral from 0 to 9 of v of t dt. So why does that make sense? Because the antiderivative of velocity is position, and then if you evaluate that from 0 to 9, you're going to plug in 9 and subtract what you get when you plug in 0. So you're just taking its ending position minus its beginning position, which is what displacement is. So for displacement, very simple. Displacement over a time interval is the definite integral over the time interval of velocity. So plugging in our velocity function, we have definite integral from 0 to 9 of t squared minus 3t minus 18 with respect to t. So we want to do antiderivative, t cubed over 3 minus 3t squared over 2 minus 18t. And all of that, we just want to evaluate from those limits of integration, 0 to 9. So we plug in the 9, we get 9 cubed over 3 minus 3 times 9 squared over 2 minus 18 times 9. So that's our first portion. And if we plug in the 0, then we get a really nice answer. We just get 0 in all 3 spots, so minus 0. And if you do all the fraction work on that, you end up with negative 40.5. So what does a negative mean for displacement? It means that we started to the left of where we started. This is position, and it was in meters per second for the velocity, so that means it would be meters for the displacement. So our displacement is negative 40.5 meters. So displacement's the easy one, definite integral from the beginning of the time interval to the end. The one that's harder is total distance, and they do ask us for that as well. So when you want to get the total distance, you just want to measure distance as positive whether you're moving to the left or to the right. So to get a grasp of that, let's look at the velocity function in a graphical form. So I clear out this stuff, clear out this old function, and enter in the new one. So we have t squared, so I'll enter x squared, minus 3x minus 18. And let's set our window, because we know that we're only going from 0 to 9. Not sure what the positions are going to look like, so I'll just do negative 10 to 10 at first, and then we can adjust that if we don't like it. So let's look at the graph. Not a very good one, so let's change those heights by quite a bit. So going back to the window, let's go from negative 50 to 50, because we weren't seeing a lot of what was going on. That's better. Now we could see it all. But what we notice on that is at the beginning, velocity is negative. And if your velocity is negative, that means you're moving to the left. And then over here, our velocity is positive and we're moving to the right. It looks like the switch point is right there at 6. So before 6, we have negative velocity, which is producing negative displacement. And then after that, we're getting positive. So what we want to do is take this section, which is going to come out negative, and calculate that with a negative sign in front of it to make it positive. And then from 6 on, we're going to want that part's going to come out positive, so we'll just add it on. All right, so let's go back with that in mind and work on total distance. So total distance is going to be making sure that all movement is measured as positive. So that first part from 0 to 6 is going to come out negative because velocity is negative there. So we'll put a negative in front of that, and that will switch that to positive. So we want to go negative 0 to 6 of v of t dt, and then plus 6 to 9, the remainder of the interval is going to come out positive already, so we don't need to change its sign. So v of t dt. So you have to break this into two separate pieces to get total distance. Wherever velocity is negative, you're going to have to change the sign of the definite integral over that region. Wherever velocity is positive, you're already going to get positive distance, so you can just leave that alone. I'm just going to go ahead and throw out the answers for you here. You end up getting 90 for this first portion, and then 49.5 for the second portion. So all we're going to do is take that that antiderivative and plug in these new limits of integration. So this is how that works out, which ends up being 139.5, and that would be meters. Just a quick comment on the relationship between the displacement up here and the total distance traveled. This part right here, if we didn't put our negative sign on it, it would have come out negative 90. So during the first 6 seconds, the particle moved 90 meters to the left. And then during the second portion, it moved 49.5 to the right. If you still had the negative sign on that 90 and added the negative 90 to the 49.5, you would get the negative 40.5 for displacement. So the difference between displacement and total distance is in displacement, movement to the left is counted as negative. But when you're doing distance instead of displacement, all distances are measured as positive. So it becomes your job to figure out where the velocity is negative and where those negative motions were happening, and putting that negative sign out front of those to convert that to positive distance traveled. All right, that wraps up section 5.3.